Today is the first session in our model eval and metrics course, and today we're just going to start to build the foundation and purpose for why we are here and doing this, and then we're going to get into introduce some of the nomenclature that we're going to need to navigate metrics throughout the rest of the course. Okay, so first we're going to start with an overview of model evaluation. And hold on one moment, I'm just going to adjust one more thing on my end. Maybe I won't. Okay, we'll just keep going till the break. I'll adjust it on the break. So what is model evaluation? This is the process of assessing the performance of your machine learning model. A lot of times you might hear people refer to this as accuracy, and I really am going to try throughout this course, and previously we said accuracy and that was okay. But now as we're talking about model evaluation, I want us to start to shift our terminology to talk about performance. What is the performance of your model? Accuracy is a very particular metric. It has mathematical meaning. And when you say what is the accuracy of your model, it means a very particular measurement. And so when we talk about assessing a model, from now on, we're going to say we're going to assess the model's performance. And I would recommend that you guys do this in your professional settings as well. It's very useful to start creating that delineation between accuracy and performance, so you can start talking about metrics that are relevant to your problem space. And accuracy is probably the most notorious metric in all of data science and machine learning, because it can be very misrepresented and misleading because it's so intuitive and we're so familiar with it that but there are so many pitfalls to it as well. We're going to learn about that, which is exciting. So why model evaluation? Why do we need to evaluate models? Why can't we just train them and then put them into production? The whole purpose of model evaluation is in order for us to quantitatively measure how well a model generalizes to unseen data, and whether it meets our objective or whether it meets our threshold or what we would expect. So model evaluation, there's two pieces. It allows us to say confidently how well it's going to generalize to unseen data when you put it into production. You can confidently say it's going to perform at 80% because of my model evaluation technique. But the other thing it allows you to do is also to compare to other approaches and other techniques and other models. So we have all these different potential competitor models. Which one is the best to choose? And that's why we have model evaluation. That was it for the review, because I think it's pretty obvious why we need to review, why we need models. But any questions on model evaluation? I guess the purpose of it. Okay. So let's go back to our college algebra course or some equivalent and just get familiar again with some of the mathematical notation that we're going to speak in as we look through some of these. So mathematical notation in machine learning and data science is used to represent these algorithms in a really concise way. So you can put something down and share it with somebody, and it's easy for them to read and understand, and it's not 18 lines of code. It's one elegantly written formula. So when we talk about functions, we have a function name, f of x is how this is referenced, and functions take an input x, and they produce some output, some x squared output. So our scoring algorithms, our scoring performance metric algorithms are functions. They are all functions. They take in y true and y pred, and they'll produce some numerical output for you based on what's going on in that function. Sorry, I should have reviewed these before because I think I know where I'm getting with this. Okay. Our machine learning algorithms are also functions. So if we think about linear regression or logistic regression, those are also functions. So a function in the context of machine learning is mapping input data to an output value or an output prediction. That is essentially all of our algorithms that we talked about in the previous class are all functions. I think that's okay. This is a little bit of a bridge between the previous class and this class, so refresher, but you guys just took that class, so I don't think you need a refresher. If we have, here's an example of a function. If we have f of x, and our function f of x is equal to 2x minus 2, when we say f at -5, then for the position of x, we now substitute that -5 value. So this is how we would pass those values to our function, and this is how our function would operate on those values or those parameters. This is, of course, very equivalent to the way that linear regression, or y equals mx plus b, works. You can make y equals mx plus b a function where it's f of x is equal to mx plus b, and then you pass x to that function. X gets substituted for this value of x here, and of course you already have your parameters, your weights and biases for m and x. So f of x and y are really equivalent when we're talking about machine learning functions, machine learning notations. Sometimes you'll see f of x, sometimes you'll see y. F of x is equal to y, which is also equal to mx plus b. They're all equal to each other. I don't think we need this one because we talked about that. This is just emphasizing that all of these are functions. So in linear regression, we can represent linear regression as a function here. We can represent logistic regression, that formula we're so familiar with, as a function here. We can represent neural networks as f of x, where x represents the multidimensional array of input. We can represent decision trees as f of x. Okay, here's the piece I wanted to get to. The other thing that we're going to, in addition to functions, we're also going to start to talk in terms of summation functions. So the reason I was talking about functions is the most common way we're going to represent that mathematically is through something called the summation function. So you guys remember summation is just taking all of the values over some iteration and adding them together. So if we have the summation, maybe, do I have an example or did I whiteboard this? Okay, I have one in a little bit. So at the top here, maybe I should start at the bottom. At the bottom here, we have the starting index. So we're going to start adding values together. We're going to start from, are we starting from 0? Are we starting from 1? Are we starting from 7? What's our starting index? And at the top, we have our final index. So when do we stop? Do we stop at 7? Do we stop at 700? Or do we stop at infinity? And then in this summation term here, this is what we're actually adding together over each of those iterations. I think this will make more sense in a couple slides. So it's often denoted by this symbol here, and it's the mathematical operation or function that's going to allow us to add a sequence of terms. And this is very common representation for our machine or our metric notation. And you might see it this way as well, where instead of being directly on the bottom, it's just to the side here, off the top and off the bottom. All right, here's our actual example. This is for you guys to work through. We have the summation from n equals 1 to 6 of 4n. Can you guys work through this and figure out what the answer would be here? I feel like I should whiteboard this afterwards. I have to keep looking ahead to see if I've... No.
Roll that over.
Yeah, actually, that would be great. Thank you. Yeah, it might need the wheels unlocked. Good deal.
You're rolling.
It looked like a rolling.
Great.
Does anybody have an answer for this one?
84.
84. All right, let's do 84. So we have the summation. The summation of 4n, where n equals 1 all the way up to 6. So this is equal to, the first iteration of this would be 4 times 1 plus, times there, 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5 plus 4 times 6. All right. And that's 81?
In theory.
All right. 81 is theory.
Running back.
No, 84. Sorry.
Oh, 84.
Kidding. Okay.
There we go. 84. Perfect. Okay. Now we are all talking the same language. That's pretty, I know this is pretty rudimentary, but it's helpful so that we're all speaking the same language as we continue. So here is the example I put on here. This is just another example. If f of n, from 1 to 4, and we have f of n, we would add 1 through 4. Okay, here's the next piece of, this is now some nomenclature. We're going to start using the terminology predicted versus actual, which I think you guys are familiar with from the previous course, but we didn't explicitly say that or define that. Here we're defining it. The predicted values are the values that are coming from our machine learning model. The actual values, or our y values compared to our y hat, these are the values that represent the ground truth data set. So predicted versus actual. Actual is going to be our ground truth representation of what's going on in the world. This is complicated sometimes because for some things, your ground truth is concretely correct, right? If we're trying to predict what price will this house sell for, we predict a price, and then later the house sells for X price, we can concretely say if we were correct or not correct on that. On the other hand, if you are trying to leverage AI or data science technology to pre-fill information into a system, for example, and that's a system that's generated with information populated by humans, your ground truth is what those humans said is the correct answer, which humans make mistakes too. So sometimes your actual, we say it's the ground truth, but that does not necessarily mean it's the global truth, like it's the real truth of the world. But for our model, in terms of our model performance, it's how we're going to assess our model. And so what you're comparing to for your actual is very, very important and worth spending a lot of time thinking about, because that's how you're going to say how well your model is doing. So the predicted values are often called y hat in machine learning models. So we have y with a little caret over the top, denoted as y hat. It represents the outputs or estimations from the machine learning models. I think that's good. And then the actual is usually represented by y. So this is quite important because when we start writing this notation, we don't have time to write predicted. We don't have time to write actual. When we start writing the formulas, we're just going to write y and y hat minus y. So it's important that you guys understand that the y hat is our predicted values and the y is our ground truth, what happened in reality labels, what we've defined as our ground truth. Okay, so here's an actual representation of that notation. This is our predicted values, our y hat, where the array, I'll say array. The array here is a series of values, a list of values, where the first y hat is our first prediction, our prediction relating to the first observation in our data set. The second y hat sub 2 is the prediction relating to the second observation, like the second house in our data set. Y hat sub n is the prediction relating to the nth prediction nth house in our data set. The actual values go in the exact same order as the predicted values. So if you compared these two arrays to each other, this is the predicted, y hat sub 1 is the predicted, and y sub 1 is the actual for the first house. Okay, does that make sense? Order matters in these. So don't shuffle or change your order of your y hat or your y. Order matters. We assume that it represents the same order of the data set, but they're typically represented as their own individual arrays. Okay. Just stop me if a question pops up. So the whole purpose for comparing the predicted versus the actual is so that we can assess the model's performance. And we can assess that across several metrics. So we have these two arrays, predicted and actual. And the way sklearn is shaped is really beautiful, by the way. It's really beautifully constructed package. And you have the same pattern. It looks and feels the same when you pass this information to all of their scoring metrics, whether it's precision, recall, accuracy. And again, this helps us understand how well this generalizes to unseen data. Okay, any questions with predicted, actual, y hat? Okay, this is all just nomenclature terminology. I'm gonna start to introduce another, I might take it, actually, we're gonna take a break here. We're gonna take a short 9-minute break, and then we're gonna start to introduce positive instances, negative instances, true positive, true negative, false negative, which is going to allow us in the later section to build to the precision, recall, accuracy, etc. Okay, come back at 7. All right. Let me take this ticker off. Okay. We had to grab our snack cart, so we're a little late getting back here. Okay, some of the nomenclature we're going to start using is referring to something called positive instances. So in machine learning, when we make a prediction on a data point and it belongs to a particular class, then that is a positive instance. We said this was going to occur, and it actually occurred. We said that somebody was going to default on their loan, and they actually defaulted on their loan. Oh, I'm sorry, I jumped ahead of myself. I went to true positive. A positive instance is when our machine learning model predicts that something is going to occur. So when our machine learning model says that somebody will default on their own. Oh, you were talking? We can't hear you. Are you trying to? Oh, from earlier. Sorry, I just saw that. Oh, I'm following you. Yeah, perfect. Thank you. Apologize there, June. So we can talk about positive instances both in terms of the predicted and the our y hat and our y. Our y can have positive instances. When did this actually occur? Our y hat can also have positive instances. The other end of that coin are the negative instances. So these are the data points in which the event or category of interest or what we're trying to predict did not occur. And remember, we're trying to think through binary classification here. So set regression aside. I shouldn't have done house prices. Set house prices aside for a second. Let's try to think about, we're trying to detect fraud. We're trying to detect spam. We're trying to predict apples, bananas, oranges. Let's think, let's start with just binary classification, 0 or 1. So negative instances are the points where the instance did not occur. Either we predicted it did not occur when we're talking about y hat, or it actually did not occur when we're talking about y. Okay, so this is maybe a visual representation that might be more helpful. Positive and negative labels here. You can see that we have the positive, sometimes referred to as the true labels. When you see these in your data set in binary classification, they will be represented as a 1. 1 always represents your true class, your positive class, your indicator class. Don't represent spam as 0, for example. That would just be confusing. That's not standard nomenclature to represent the instance of something not occurring as 1. Always represent the instance of something not occurring as 0. It just feels more natural to us. That is either 0 or false. False, it did not occur, or otherwise referred to as a negative instance. Now, just because they're negative and positive, if we think about fraud detection or spam detection, of course, your positive class here is going to be smaller than your negative class. And generally that's true. Most of the time your negative class is in binary classification is the larger proportion of your data set, but that's not always true. Your positive class isn't always your smallest class necessarily. Okay, we know binary classification, but this is just a reminder that binary classification problems, there are 2 classes, typically denoted 1 and 0, where a 1 is the positive class and 0 is our negative class. Positive instances are situations when that condition happened or that event happened. We did find that they had breast cancer. We did predict they did have diabetes in our diabetes data set. They did die on the Titanic in our Titanic data set. So that event did occur, and then the 0 would be those events not occurring. When we think about multi-class classification, this in this situation, we can have multiple instances. So instead of just 0, 1, we can have 1, 2, 3, 4, 5, 6, 7, all the way up to n. So in our image data set, remember we had numbers from 0 to 9, so we had 10 classes. So the positive, when you're thinking about positive and negative instances and how they map to multi-class classification, the positive instances for digit 3 are when images of digit 3, and positive instances of digit 7 are images of digit 7. I think I can whiteboard this if, I'm not sure if we're talking about that. I might have a visual for this a little later. Imbalanced data, as a reminder, is when one class is significantly larger than the other. Typically anything greater than 60% is going to cause class imbalance. And handling this is very important because it can be misrepresented in our metrics, especially things like accuracy. Class imbalance can cause accuracy to be very misrepresented. So we'll talk about that. We'll walk through that as a particular example. Okay, now we can talk about true positives. And this is, we're going to talk about true positives, false positives, true negatives, false negatives, not particularly in that order, but these are very, very foundational to all of the binary and multi-class classification metrics that we're going to talk about. So if there's something that I would say you should focus on and spend some time really understanding, it would be these foundational representations, because it's going to be easier to understand all the manipulations of these metrics later. Just a small anecdote, for example, I was working with a problem the other day where I had to detect how missing information was, but I wasn't working with, I was only working with a couple of these values. I was only working with false positives and false negatives. And I actually rewrote myself a mathematical formula that enabled me to create a missingness metric represented to what I was actually trying to detect, because I understood these and I understood how F1 score worked. So sometimes they are useful, and you can, even though it feels very rudimentary, there's still ways you can manipulate these into your metrics today. And okay, that was enough fluff talk about how cool these are. So true positives. This is exactly what you want to happen. This is when you predict something and you were right and you get a pat on the back. So true positives are the times when you said there was breast cancer and there was breast cancer. You were truly correct. You said that this was an instance of fraud, and it actually was an instance of fraud. So these are the times when the model correctly predicts a positive instance, a 1, this is going to happen, and it actually does happen in reality. False positives is when the instances are classified as belonging to, I want to make sure I say this correctly, hold on. We falsely said that it was a positive instance. So we incorrectly, falsely said that it was a positive instance. So these are the situations where we say that somebody actually has the disease, but in reality, they actually do not have the disease. So we say that this is spam, and in reality, this is actually not spam. So we are over classifying. Okay, these all sound really similar, so they can be hard to differentiate. So true negatives. So the first word, the false or the true, tells you whether or not the model was correct, and then the second word, the positive or the negative, tells you what the prediction was. So true, negative. So we we truly predicted negatives. We correctly predicted negatives. So when we said this instance wasn't going to occur, and in reality, it did not actually occur. This is the one that gets you into trouble with accuracy, and we'll see that. Because if you look at these class imbalance problems where there are many, many situations of not spam in your mailbox, many more situations of not spam, you can artificially weight your metric to look like your model's doing better than it is by considering all the true negatives. Yep, you said that wasn't spam. It wasn't spam. Good job. You got that correct. We'll see that actually come through in the formulas. The last one here of these 4 categories is false negatives. So you falsely said that it was a negative. You incorrectly said that it was a negative. You said it was negative and it was not correct. So false negatives are situations where the patient actually did have the disease, but you said that they didn't have the disease. So you said, oh, you don't have diabetes, and then you find out later actually they did have diabetes. So not a good situation. These are the only 4, the combination of these 4 outcomes are the only outcomes you can have in terms of least binary classification, and an extension of this works for multi-class classification. So you're one of these 4 categories. You have to be a true negative, a false positive, a false negative, or a true positive. So I have the predicted negative, actual negative, predicted positive, actual positive. That's the true negative, true positive. Then we have our false positives, which is where we're saying there's information, or we're saying that this instance occurred and it didn't. And our false negatives, we're saying it didn't occur, but in reality it did. Here's your fun visual. So true negatives, we can, we said this is clearly a pizza, and we said it's not a hot dog. It in fact is not a hot dog. And there are true positives. This is a picture of a hot dog, and we said it's a hot dog, and it in fact is a hot dog. Our false positives, we said this was a hot dog, but it's not a hot dog. It's just a dog as a hot dog, which is not a hot dog. So we said it was a hot dog. It's not a hot dog. We got that wrong. These false negatives, this one we said was not a hot dog, and it actually is a hot dog. It just looks different than other hot dogs. It's a chili dog. And so these gray boxes are the situations in which our model is wrong. The blue boxes are the situations in which our model is right. So if you are accuracy is correct predictions over all predictions. So it's blue boxes over all 4 of these boxes. Okay, calculate the true positives. Here's your first working example for class. We have a binary classification model. Our model predicted 1, 1, 0, 1, 0, 0. The true values were 1, 0, 1, 1, 0, 1. Calculate the true positives, false positives, true negatives, and false negatives. I'll give
True is
you
1, right? I assume that's typical. but
true
it's
positives or negatives.
Positive, sorry. Positives is 1 and negatives is 0, right?
True positives is more than 1.
No, sorry.
The number of
Positive is represented by 1 and negative
Oh,
is represented by 0.
thank
I'm
you.
reading this very badly.
No, thank you. Oh, I apologize.
I'm like, that should be typical, but I'm verified.
Yes,
Okay.
positive instances are represented as a 1. Negative instances are represented as a 0. And I would recommend you guys always adhere to that standard, or it gets really confusing when you share your code with other people. I've seen that done before, and it is super confusing.
Let's just try to describe that.
I thought you were asking how many true positives there were in that example, if there was only 1. We're moving right along, guys. We might start on the next section, content. We'll just see how far we get. All right. Jean said, I'm going to read Jean's answers. Have 2 true positives. We have 2. That's correct because we have 1 here and 1 here. Sorry, they're not exactly lined up. To do some visual work. And then false positives, 1. And that's correct. We have this false positive here. And true negatives, 1. So we have 1 true negative right.
Second to last.
Oh, sorry, wrong one. Right here, true negative right here. I started going to the next one. And we have 2 false negatives. So this is a false negative here, and this is a false negative here. That's exactly right, Jean. Is that what you guys had too? Perfect. All right. This is just a summary of our mathematical notation. I think we're still in the mathematical, notation section. So this is just a summary of our what you need to know, like background on mathematical notation. That's maybe a strong way to phrase that, but be familiar with y, and y sub I and what that represents, y hat sub I, what that represents, f of x, summation notation, understand true positives, true negatives, false negatives, understand positive instances and negative instances. That's the nomenclature we'll use moving forward. And this will help you as you're reading stuff too. This is how people will talk about it. Okay, now we get to talk about the cool stuff. We did all that. We're through all the intro stuff. And now we get to talk about performance metrics for classification problems. So in this class, we're going to start first with classification problems, just like we did in the machine learning algorithms course. We're going to start with binary classification. We're going to build a concept and understanding for that, move to multi-class, and then we're going to move to regression and start talking about loss. So it's a little different because in the other class we started with regression, but here we're going to start with binary classification. Accuracy, the notorious accuracy. It's really probably the most popular metric in all of machine learning because it is so intuitive for people. When you tell someone what was the percentage on their course, on their grade, how accurate was was your pitch, and it's used so many places, and it's so intuitive for us to think about number of correct responses over total responses, and it's usually, because of that, it's represented on a 0 to 100 scale, or 0 to 1 scale, depending on how you multiply it. And so people really like it. It can be very powerful metric for communicating with business and with stakeholders because it's very intuitive to people. But it measures the proportion of correctly classified instances over all instances, all predictions made. So here's your formula. Correct predictions over all predictions. It's really simple. It's really straightforward. It looks and feels intuitive. And it's, again, everybody knows what accuracy is. You talk to your parents, your sisters, your brothers, your aunts, your uncles. They all know what accuracy is. Now that we've talked about true positives, true negatives, false positives, false negatives, we can rewrite this formula. And we can rewrite it in the context of those variables. So when you think about the denominator here, all correct predictions, what that really is all of your true positive instances plus all of your true negative instances. So all of your trues. So all the times that you said somebody had breast cancer and they actually had breast cancer, all the times you said somebody had breast cancer or said somebody didn't have breast cancer and they actually didn't have breast cancer. That's your denominator. And in your numerator is everything, including those two things. So true positives, your true negatives, your false positives, and your false negatives. All right, here, calculate the accuracy. So we have a binary classification problem where we're predicting the emails are spam. We're predicting them to be labeled as positive class 1 or not spam, negative class, which is labeled as 0. We have a data set with 100 email samples, and our model predicts whether each email is spam or not. Let's imagine that we correctly classified 85 emails. 50 of them we classified as spam. These were our true positives. We had 50 true positives, and 30 of them we correctly classified as not spam. Those are our true negatives. What is our accuracy? There you go. Okay. It wasn't a trick question. Cool. We understand accuracy. So 85% because we have 85 correctly classified emails over 100 emails total that we made predictions on. So, I even have it on the next slide. So it's our, we take our true positives plus our true negatives. If we want to use that detailed formula, 50 plus 35 is 85. That's the number of correct predictions over our 100, and that's 85% accuracy. I've already sort of talked about the pros and cons here, but just to reiterate, super intuitive, really easy to understand. The calculation is very simple, and it's fairly comprehensive, meaning it can be used in a lot of dynamic situations. It's applicable to many, many things. The things that are going to get you with accuracy is that it's very sensitive to class imbalance. It doesn't perform well with class imbalance situations. So for example, let me see if I have an example. Nope, I don't. And it's also, I'm going to come back to that. It's also insensitive to misclassification costs, the cost of misclassification, and it's not able to really predict the confidence of the prediction, which is fine. None of these metrics are that we're going to talk about today. The sensitivity to class imbalance. I want to give a particular example here. So let's go back and look at our formula here. True positives, true negatives, false positives, false negatives. Maybe I'll just spend 2 seconds whiteboarding this. In the future, I will put a slide in here. So imagine we're working with a fraud data set, spam, whatever, something with heavy class imbalance. Let's just do fraud. There's a lot of companies that do fraud. So we want to say, hey, is this person committing, credit card fraud or loan fraud? And in our, let's say, 1% of our customers commit fraud. Okay, so we have 1% of our customers that commit fraud. That's our ground truth. We know that. That's our that is in our Y data set. So we train a model, and let's see how well our model does if we never predict a single instance of fraud. So let's create a model, and let's say our model, it predicts 0 for everything. Okay, let's see what our accuracy is. Accuracy is equal to true positives plus true negatives over true positives and false negatives. So our true positives, we have 0. There are no situations in which we said that there was fraud. We predicted 0 for everything. So our data set's going to look like Y hat Y. So Y hat is 0 for everything, and let's say Y is 1, and then Most of these others are 0. Our true negatives. What are our true negatives? Assume there's 100 customers. How many true negatives do we have?
99.
That's it. So we have 99, and then we know that this bottom one is 100, right? We have 0 plus true negatives, which is 99, plus false positives. We never made any positive predictions, so you can't have a false positive, and then false negatives. We predicted 0 for anything, so we can't have a false negative because there's no situation in which we predicted 1. So,
False negative one.
nope, that's 1. That's 1. Whoops. Because that was this situation, right?
Yeah.
Thank you. All right, so now we have 99 over 100, and our accuracy for our fabulous model that predicts 0 for everything is 99%. So a really good model, huh? Really, really good model. Here's the thing. You want a model to detect fraud, and this model will never detect fraud, ever. So there's my example for how accuracy is, it can be notoriously misrepresented metric. If I told somebody that I had a model that performed at 99% accuracy, that sounds really good. But in this situation, it will never do what I actually want it to do. Okay. I beat that with a dead horse, so. Precision. Let's start to talk about something that's not accuracy and true positives, false positives, true negatives. So we can talk about some of these metrics now in the context of our true positives and false positives. So precision is measures the proportion of true positive predictions among all positive predictions. So it's true positives over true positives plus the false positives. So this is saying when your model predicted positive, when your model said that somebody had cancer, when your model said that it was spam, how many times was it actually correct? So when it said there was spam, how many times was it truly correct? So how precise, how tightly coupled are those predictions to each other? So it really assesses the quality of your positive predictions in your model. So it's a proportion of positive instances over all predicted positive instances. Okay,
If
so
it was a scenario like you just did, where
Yeah.
you had no positive. Okay, never mind, I'm fine. I thought about 0 on the bottom, no 0 on the top, never mind.
no, that's good. Let's write it out because that's
Is your precision of 0?
let's
That'd be weird.
Let's do this. What's the precision here? It's, go back to our formula. Sorry, I lost my mouse. There we are. True positives over true positives, false positives. So true positives, we had 0 over true positives was 0 plus our false positives was 0, right? We only had
0. Wait, no. Wait, yeah, because that's a false negative.
Yeah, because this is a false negative, right?
Right.
So like, how is it?
In A.
Well,
How would it come out?
it should be 0.
Okay.
Yeah, you can't just divide by 0, but they're inside of the code. There will
Okay,
be
they
situations
have
that
these
handle that. Yeah, it's a good question though. This is the whole point of this course, is to work through exact examples like that so we can really start to understand these. So this is the quality of your model's positive predictions. When you say it's good, how good is it? How good is it? And when you say this happened, how good is it actually at saying that happened? So this is relevant because it's very important in scenarios when the cost of a false positive is very high. So I'll use this scenario a couple times because this is relevant to both precision and recall. But imagine somebody's coming into the doctor's office and you were testing them for cancer. And imagine you told them they had cancer and they actually didn't have cancer. the cost of a false positive is very high. That's very traumatic, and that is a lot of emotional tax to put onto somebody. And so when we really care about the precision, when we're very sensitive to making an incorrect positive prediction. Let me see if I had any. I think I used the same example on this slide. Yeah, any medical condition, for example. So a high precision indicates the model makes very few positive predictions that are wrong, very few incorrect positive predictions. When it says it's fraud, it's almost always fraud. So that's what precision represents. Conversely, a low precision may indicate that the model is, a lot of times when it's saying it is this instance, it's doing that incorrectly. And there's almost this trade-off that you'll see between precision and recall, which we'll talk about recall next. And there may be certain situations, which I'll talk about in recall, when you want the model to be better at one versus the other. Here's a concept check. Which types of predictions, and when I say types, I'm talking about true positive, false positive, true negative, false negative. Which of those classes are not considered in the precision metric?
True negative, false negative?
True negatives and false negatives. So those are not considered at all in precision. It's not part of the metric.
Is there a precision version for the negative side? Like, like comparison, like seeing what's the quality of the negative assumptions or negative predictions?
There is not. You could just use precision and then invert the values, but there is no particular metric that's usually used. Actually, most people try to ignore the negative instances in most situations and not include them. So, all right, so here's precision. Out of 100 emails, so this is the same example. You have 100 emails. Our model predicts 50 are spam. And out of these 50 predicted spam emails, 40 are correctly classified as spam, and 10 emails are not spam. Those are our false positives. What is the precision? What do you guys think?
8%.
Nice. There we go. So it's just the 40, the ones that we correctly said were spam. We predicted as spam. They correctly were spam over all the instances where we said something was spam. So the 40 plus the 10. So 40 out of 50 is 80%. Okay, here's the partner metric to precision. The other end of that coin, so to speak, is called recall. So this measures the proportion of positive instances, true positives, over true positives and false negatives. So this measures the proportion of instances that were correctly identified. So what this looks at is, out of all of the people that actually did have breast cancer, how many did you find? So there's, in our ground truth data set, there were 30 people that had breast cancer. How many did you predict as breast cancer? You predicted, 15? Okay, so that's 15 true positives. So 15 over 15 plus, that means you missed 15. That means you had 15 false negatives. That means there were 15 people that you said didn't have breast cancer. You predicted 0, but in fact they did. They were actually a 1 in our actual ground truth data set. So recall is how many did you get out of that entire set? So recall has a couple other terms, just so you know, as you peruse. It may also be called sensitivity. It may also be called the true positive rate. I will always use the word recall in this class, but just as you're looking on the internet and reading things, those are the same. Those mean the same thing. And recall really measures the completeness of the positive prediction. So precision measured the quality, how precise or the quality of the positive prediction. This measures how complete, how much of the pie did you get? So the relevancy of recall is that it helps us measure, did we catch everything? Or are there some things that got away? Are there some things that escaped our model's detection when we're thinking about positive predictions? And it's really important in scenarios where the cost of missing something is very important. So for example, I'll use the medical example and then I'll give you a different situation in which I've used recall. So for example, in the medical domain, it's the same example. If you are telling somebody that they don't have a disease, but then later they get sicker and it gets worse, and then they realize they do have the disease, that is a false negative. And that is what recall is trying to capture. How many times does that happen? The other example that I've actually used this for is we had a document that could have a bunch of different comments put into it. And based on what comment was made on this document, it would route to different teams to take action on it. So it's like a contract document. And did legal need to take action on it? Did HR need to take action on it? Did sales need to take action on it? So there were 9 different teams that potentially, based on the content of this comment or request, might need to take action on it. So they preferred that we over-notified people and that teams who actually didn't need to take action on it still got a notification that they needed to take action, as opposed to only notifying people when they really needed to be. So we weighted recall higher than precision. And we leveraged something called an F-beta score, which we'll talk about. So that, yeah.
The medical one's interesting because there's also the example for.
I know, I need to come up with a different example. I know, that was
That's all
terrible.
it is. Medical needs to be perfect.
Yeah,
So the high concept, don't do it, high concept, you do it.
so how do you balance that? That's a
Yeah.
real challenging question. Which scenario is worse? I won't answer because I don't know, but
Recall being off of that one.
recall's pretty bad.
I'd rather just be stressed out.
I don't know, I would consider recall more important in deciding if you needed a test, while precision more important in deciding you needed treatments.
Yeah,
So especially like treatments that have a negative impact on you, but like
yeah,
whether you want them to be for sure, okay, yeah, you need another test, and maybe it's more expensive, maybe it's more time consuming, you can have some damage, but like,
It's
it's that
not-
new test.
Right, that's fair, yeah, makes sense.
And
That's how I do it, but.
that's why people always say get another opinion or run another test and run multiple tests. Because even if it said it didn't happen, or even if it said it did, you guys know statistics. You're statisticians. Like there's a percentage of the population who get misclassified. So, okay, interpretation. This, if you have high recall. So what does it mean if you have by the way, as we walk through these metrics, for each one we'll talk about what does a high value mean for that? What does a low value mean for that? For recall, if you have a high recall, that means you're catching most of the fish. So that means that you're really minimizing your false negatives. You're minimizing the times in which something occurred and you said it didn't occur. Conversely, a low recall might mean that you're missing a lot of situations. You're missing a lot of positive instances. They're going by and your model's not catching them. So you're going to have a lot higher false negatives. And like I said, you'll see that precision and recall are sort of a trade-off of each other. As you get much, much better precision, you're going to have worse recall. And as you get much, much better recall, you're going to have worse precision. And there's actually a metric that quantifies the two of those, which we'll talk about. Okay, same example. You've got 100. It's not emails this time, but now we're working with patients. I'll always do these out of 100, just so you know, it's easier. So you got 100 patients, and 60 of the patients actually have the disease, and our model correctly identifies 45 of them as positives. However, our model misses 15 patients who have the disease and incorrectly classifies them as negative. What is the model's recall? All right, what did you guys have?
25%.
Nice. That's exactly correct. So we have the 45 that we correctly identified as positive instances over the 45 plus the 15 that we missed, the 15 that we said did not have the disease, but they in fact did. And that leads us to a recall of 75%. Here is a nice, I like this visual cue. People learn in different ways and different types of, excuse me, I have to cough, one moment. I'm gonna mute so you guys don't hear that. Okay. Different types of visual aids resonate with different people. So here's one, I like this one quite a bit. On the left here, we have all of our predicted outcomes, or all of our positively predicted outcomes. And on the right here, we have all of our negatively predicted outcomes. So all of our zeros that we predicted, that those are the open circles. And the ones are the full circles. Inside of this circle here, you can see that in green, these true positives, these are the situations in which we were correct. So we predicted it positive, and it in fact was positive. The false positives here are when we predicted it positive and it in fact was not positive. We can see that the example was actually negative. So this circle here is what our model predicted as 1. So the circle is what we predicted as 1, but the this box here represents the ground truth of what actually was 1 versus what actually was 0. I have to sneeze too. Oh my goodness. So over here, you can see our visual representation for precision is this green slice, true positives, over the green slice plus the red slice. So remember, I said this circle here was just the model's predictions. You can see that this precision is only concerned with how the model is predicting. When it predicts it's green, how well is it predicting that it's green? And when it predicts the closed circle, how well is it doing? It's only concerned with the model's predictions. Whereas recall, you can see is only concerned with the left half of this visual aid. So it's only concerned with the times in which, for which a positive instance exists. which is this left half of the visual. So it's the green slice, the half green slice of the circle, over the half green slice of the circle plus this outer box here. But you can see that it doesn't touch any of the negatives at all. So we're only concerned with the recall of the positive instances. Okay. That's a visual cue, just a different way of thinking about it, continuing to wrap your head around it. Additional resources, here's another, here's a page that I think describes these things well. And in fact, I believe many of these graphics, such as these formulas, are pulled from that particular page. Oh, look, that was it actually for this initial slide deck. And we are at 7:48. Guys, we got a whole nother hour. We're going into the second section. Any questions so far?
So will all the metrics not care about true negatives?
No, because accuracy cares about true negatives.
Does it? It just does everything.
It does everything, which when you have a high proportion of true negatives, they get a lot of credit, basically. They get a lot of airtime in the representation of that metric. I am just going to download this other PDF real quick. Oh, I downloaded the wrong thing. Presentation. Oh, I might have skipped right over our breakouts. We're going to do a breakout. I did. We're going to do 2 breakouts back to back. Right when we get back from the break. I'll drop these breakouts to you guys. You can start working on them. Sorry, I skipped right over them. I was supposed to look back at this agenda. We will, I'm going to drop these breakouts in the Slack channel. And later it will be on the Google Drive. We're going to do a summation function and then introduction and then implementing an accuracy function. We're going to do both those. So it says implement the summation function discussed in class. You can do any one you want. You can do 4n, for example, is one that we talked about. You can make it fancier than that if you want.
Should we do this on Colab or whatever?
Whatever works for you guys. And then let me look at this other one. Yep, and in the other one, I'm asking you to calculate your own, create your own accuracy function. I already wrote a function to give you true positives, false positives, true negatives, false negatives. So you can, the idea is for you to leverage that. Create your own accuracy function using true positives, false positives, true negatives, and false negatives with that accuracy formula. All right, we're gonna go through these code pieces first, and then after that, I'm gonna give you guys an option. We can either continue on through section 2. We can talk about confusion matrix, F1 score, and F beta score. Or we can just have open discussion time to talk about honestly anything modeling related, but probably focusing on metrics and implementation, and we can dive into situations in which things have gone wrong, situations in which things have gone well. Up to you guys. We haven't had discussion time yet, and I would like to build those in at some point, but totally up to you guys. We just had extra time, so up to you how we leverage that. But first, let's go through these notebooks, and give me just a moment while I pop that into a Colab location. Actually, I think they're already, I should be able to. Oh, it's the wrong one. What did you guys do for your summation function? Would anybody be willing to share their code for the summation function? So here, here we have, I guess this does the summation, and then we said, hey, take I to the 2 and print the results of the summation function. What did you guys implement for your summation function here?
So I defined and called a new term function. Very
Nice.
Very clever technique input of I. And I just did the one we had, where it was return 4 times I.
4 times I?
Yeah. And then pass it into write a new variable called new result. I could copy paste this.
No, this is good.
New result equals summation 1 to 5 with new term function is the last argument. Thank you. How many did you do?
I did 6.
Was it 6? I think
Yes.
it was 6.
6.
Okay.
Perfect. All right, we're gonna see your results here. We're gonna print new results, and oh, nope, I didn't run anything. Also, I'm gonna have to delete this because this is in the class folder. Yeah, which is not great. Nobody look at the history. So the answer is 84. So let's confirm our answer. Did you do something similar?
Same thing.
Same thing.
Only
Perfect.
difference is I call it class function, so
Perfect.
Ooh.
big difference.
Well, if we're getting fancy here, I put mine into an F string at the end. So
Oh, that is
I printed
fancy.
it and gave it, I think it gave us its summation result.
Yeah.
That's about it. I'm doing.
Jean, did you had something similar? And we're gonna look at this other breakout as soon as that one loads. Perfect. Okay, now we're gonna look at accuracy. And in this one, created a function that determines your true positives, true negatives, false negatives, given a data set. And what did you guys do to create your accuracy function? Def my accuracy. Oh man, this thing just gives it all away.
You know, that you can pass true, positive, false, positive. True,
Yeah, you
negative,
do.
False, negative, and then you do the formula.
Yeah, so I didn't even make a function. I didn't even follow it. But
Oh, I did a straight return. True positive was true negative divided by, true positive was false positive was true negative was false negative.
That's exactly correct. So this would be, you could just, do the positives divided by all the instances, but I asked you guys to leverage particularly the true positives, false positive, true negatives, false negatives, because that's what we were talking about today in class. So this would return the accuracy. And if you did it the other way, you should be able to do it this way, then compare to that accuracy, and you'll see that they're exactly the same. I'm going to delete this again just because this is the class notebook. So, okay. I also have to feel like I have to sneeze again. Decision point for you guys. Would you like to go through confusion matrix, F1 score, F beta score, or would you like to have just open discussion? Makes no difference to me, so we're all the same.
Do you want to start with open discussion and see
Yeah.
how well we go?
Let's
We might end up
do
going back into it.
Let's do that. I am going to shut off the recording. I think I can always turn that back on if we go back into it. So I'm going to end the stream. One moment. And I'm going to end this now.